Should we start?
Yeah, feel free to start.
Is that David?
That's David.
David, is there a step stool where we can change the clock?
Afterwards.
No, afterwards. Okay.
All right, good afternoon, everybody. Welcome to today's EECS colloquium. Thank you all for coming. So I'm really delighted to introduce today's speaker, Professor Wesley Holliday, who is a professor of philosophy right here at UC Berkeley. I've known Wes for many years, over a decade now, as a fellow member of the graduate group in Logic and the Methodology of Science, which goes by Logic Group. And Wes currently serves as the chair of the Logic Group. So this is an interdisciplinary group that includes EECS, as well as the departments of philosophy and mathematics. Wes got his PhD from that other university across the bay about more than a decade ago. And his PhD actually received one of the top prizes in the field of logic. It's called the Beth Dissertation Prize. And then since then, he's been working here at Berkeley in the intersection of logic and philosophy and social choice theory. And a lot of his work over the last several years has had very tight connections to computer science and engineering and principles of many theoretical topics here in EECS, and also overlaps with some of the more practical tools from fields like formal methods and programming systems and computational logic. And so I'm really excited to have Wes here. Some of his work also applies to ethics and AI safety, and so it's a real pleasure to have Wes here and to tell us more about the links between computing and social choice.
Thank you so much, Sanjit. It's an honor to be here. As Sanjit said, I work in logic and also in social choice theory. Today I'll be talking about the social choice side of things. And I'll be talking about an area that's very vibrant, I would say, called computational social choice, aptly named. And so what I'm going to do is I'm going to start by giving a kind of crash course on basic social choice, and then I'm going to talk about connections between the two sides, and then I'm going to talk about some open problems at the end. Okay. So here's a basic social choice kind of problem. It's a kind of preference aggregation problem. So we have some set of candidates or alternatives. They don't have to be political candidates. They could be public policies or actions, something like that. And then we have some number of voters, and they give us some data. In this case, I'm assuming that the voters give us rankings. This is my favorite option, this is my second favorite, and so on. Then what we want to do is we want to take all that data and aggregate it into some collective output. Maybe like a social ranking of the candidates. If you're in a faculty hiring committee, all the committee members have their own rankings of the job candidates, but we have to send a common social ranking to the administration, for instance. That's the kind of problem that we're interested in. But there can be many different types of outputs that we provide. We could just give a subset of candidates saying, these are the candidates that we want to hire, but we don't have to rank them. You could pick a single candidate, but sometimes there's ties, so you might want to allow multiple candidates. Also, we can consider other type of input formats. So instead of giving a complete linear order of the candidates, maybe a partial or truncated linear order. In actual political elections using ranked ballots, I think legally it's hard to require people to rank all the candidates, although maybe in some countries they require that. But here in the United States, you can just give a partial ranking, say BA, and I don't want to rank the other candidates. There's some applications where you want to allow voters to express ties between candidates. So it doesn't have to be a linear order. It could be like a strict weak order, something like that. And I should mention another thing is, you might want to output not even a ranking, but maybe like a probability distribution over the candidates, and then you have some mechanism that selects according to that probability distribution. So there's lots of ways to set up this framework. You don't even have to give rankings. You could have kind of choice functions where you ask people to make pairwise choices. You could try to ask them which are the candidates that you approve of. So that's something called approval voting. That's a different input format. You could ask or somehow elicit numerical utilities, either by looking at their revealed preference, their choice behavior, or just by explicitly asking them to give numerical ratings. So these are all variations of this kind of preference aggregation problem. Okay? So this is sort of like when Kenneth Arrow did his Nobel Prize winning work on this social choice aggregation problem. He was roughly in this setting where you collect rankings from the voters, and your goal is to come up with a social ranking. It's called that a social welfare function. And how do we evaluate how good the collective decision procedure is? Right? There's many, many options for how we do this aggregation. We can evaluate them by stating precise principles that we would like a collective decision procedure to satisfy. You can call those criteria or axioms, and check whether the voting method satisfies the axioms. You can also prove results like this is the unique collective decision procedure that satisfies axioms X, Y, Z. So I come from logic, so that kind of complete axiomatic characterization really appeals to me. But there's other ways of evaluating these things. I mean, there's a kind of game theoretic perspective that looks at how manipulable the voting method is. So as I'll discuss shortly, basically any reasonable collective decision procedure sometimes gives voters an incentive to misreport their preferences, to thereby get a better outcome according to their sincere preference. Okay, so that's a game theoretic kind of perspective on the voting problem. We can also think about what's the computational complexity. We want to make this practical, that we can actually compute the social ranking or the winners.
You vote in such a way so as to game the selection.
Exactly right.
Yeah.
It means rather than submitting your sincere preference over the candidates, you submit an
Truth-telling, but
you submit an insincere preference in order to achieve an outcome that is preferable than what you would have achieved had you submitted your sincere preference. By the way, I welcome the clarification questions during the talk. I usually say save all the devastating objections to the end.
Okay, actually, so, and logistical point, please use the mic.
oh, you got to use the microphone.
Who's the?
So could you please clarify what you meant by axiom satisfied?
Yeah, I'm going to give examples of this later.
And also what are instances where say voters would be incentivized to do something to express an insincere preference to get their sincere preference?
Yeah. Okay, let me start with the second question first. A simple example would be like in plurality voting, where the only thing we care about is the person's first choice. Okay? Somebody who believes that their favorite candidate is unlikely to win, let's say their favorite candidate is a third-party candidate, and they think, sadly, my third-party candidate has no chance of winning. Even though they are my favorite, I'm actually going to rank one of the major party candidates in first place because that way maybe I change the election outcome in a way that I prefer. Does that make sense? That's an extremely simple example of it. But with more interesting voting procedures than plurality voting, where you actually take into account more of the ranking than just the first place vote, then there's all kinds of interesting manipulation strategies that you could do. Like bury the rival of your favorite. Even though you really like D, you actually bury D at the bottom of your ranking, thereby changing what the voting rule will select as the winning candidate in a way that you prefer. Does that help on the second question? And the first question, let me just give you examples of axioms later. It's basically just a mathematically precise principle that you want the voting rule to satisfy.
Another point of clarification: are there any complications with respect to the relationship between the set of voters and the set of candidates, disjoint, one very much larger than the other, or equal in a sense?
You can consider all those settings. That's the beauty of this kind of abstract mathematical framework, is you can consider all those settings. Often it's of interest to take the set of voters, like in a political context, to take the set of voters to be large and the set of candidates to be fairly small. But there's lots of other applications of social choice where the set of candidates might be infinite. So I'm leaving that open at the moment. Thanks. Okay. There's other ways to evaluate. So something that happened in political science and more recently in computer science has been an interest in, if you have an ordinal voting rule that just takes ordinal information from the voters, but you suppose that the voters have underlying utility functions that generated these ordinal rankings, then you can ask, when you, let's say, pick a winning candidate, how well does that winning candidate do in terms of social utility, like aggregate sum social utility, according to the underlying utility functions that generated these rankings? So there you might have a certain probability model for generating utility functions, which then induce ordinal rankings, and then you run your voting rule, pick a winner, and see how good your winner is from the point of view of social utility. So there's a kind of worst case analysis of that called distortion in computer science. And earlier in the political science literature, they were interested in kind of average case social utility under somewhat plausible politically probability models for generating voter utility functions. Okay, I'm going to come back to that. If that was a lot, I'm going to come back to that a little bit later in my talk. So there's other ways of evaluating these things. I just want to say that there's a multi-dimensional way of assessing how good one of these collective decision procedures is. Okay, so for concreteness, I'm just going to give you an example of a collective decision procedure that I've studied with my colleague Eric Packett, which is called split cycle. I think it'll appeal to the computer science community. So just a little bit of mathematical setup. So I want to allow elections to have different numbers of voters and different numbers of candidates. So up front, I just fixed these infinite sets, V and X, of voters and candidates. Any particular election in my talk is just going to use a finite subset of the voters and a finite subset of the candidates. Okay.
Countably infinite or?
It doesn't matter for this talk. Make it as big as you want, yeah. So just some notation, if I have a set X, I'm interested in the set of what are called strict weak orders on X, which are just rankings that allow ties. Okay, that's all that means. And then a preference profile, or a profile for short, is just a function that assigns to each voter in some finite set of voters that we selected a ranking allowing ties of the candidates from some distinguished set of candidates in that election. Okay, so for a profile, we have a set of voters, we have a set of candidates, we assign to each voter a ranking over the candidates allowing ties. If you want, you could disallow ties, but let's just set it up like this. In fact, here's an example without ties. I've anonymized the profile. I just tell you how many voters had each of these rankings. So this means 2 voters submitted the ranking, B is my favorite, A is my second favorite, then D, C, and so on. Okay? A lot of voting rules don't actually care about the identities of the voters, whether it's Anne or whether it's Bob. They're anonymous, so they only care about how many voters of each type you have. So I need that notion. That notion of a preference profile is going to be super important. Okay? Is that clear? The columns are the rankings. And this is how many voters submitted this ranking. The profile is the whole thing. Thanks. Okay, the next notion I need is, of course, we're interested in, if we take 2 candidates, we're interested in the number of voters who strictly prefer candidate X to candidate Y. That's what this notation means. I'm just counting, this is cardinality of the set of voters who strictly prefer candidate X to candidate Y. Okay? And then I need the following notion. The margin of X versus Y is the number of voters who ranked X above Y minus the number of voters who ranked Y over X. So if this is positive, then X wins head-to-head against Y in just a head-to-head comparison. How many people prefer X over Y? How many people prefer Y over X? If it's more people preferring X to Y, then X wins the head-to-head comparison. What that means is you can make a weighted directed graph where the edge relation, this is in fact the margin graph of that profile. And what this means, I can kind of highlight, is let's look at this edge. This means B beats D head-to-head. More people rank B over D than vice versa. You can compute that from the preference profile. Just don't forget about these numbers, how many voters submit each one. So more people prefer B to D than vice versa. By what margin? By a margin of 1. So there's 1 more person who ranks B over D versus the number of people who rank D over B. Okay, so this is just an asymmetric directed graph, because if I beat you, you can't beat me. An asymmetric directed graph with these positive integer weights.
So wait, in your table, the first is the least preference?
No, this is my favorite. Sorry, this is my favorite.
So
does that make sense?
These 3 people rank
Yeah.
D above B. B above D.
Yeah, D above B are the red people. D above B, D above B, D above B. So that's 2, that's 4. Yeah, and then there's 5 who prefer B to D. That's how I get the margin of 1.
I didn't see the number.
Yeah, sorry, you got to definitely look at the number on top. Okay, and I should say that there's a way of going back. That is, if you have an asymmetric directed graph with integer weights, then there's a theorem, de Boerd's representation theorem, that says we can build a preference profile that may involve having ties in the rankings. such that your initial directed graph is the margin graph of that profile. So there's a representation theorem. And if the parity of the edge weights are the same, like in this case, the parity is the same, they're all odd, then you can actually make a profile with linear orders without ties, such that your graph is the margin graph of that profile. What that says is that any kind of craziness can happen. So like there's a lot of cycles in this graph, right? So this is why the voting problem is difficult. If you could guarantee that there was always one candidate who beat every other candidate head-to-head, then you might say this is an easy problem. You just pick the candidate who beats everyone else. That's very intuitive. I'm going to come back to that idea later. The problem is that's not guaranteed. So you can have these majority cycles where a majority of people prefer C to B, a majority of people prefer B to D, and yet a majority of people prefer D to C. Okay, this is called a majority cycle or a Condorcet cycle. I'll come back to the name Condorcet in a little bit. So these weighted directed graphs are going to be very important for my story. Okay, I better speed up here. So a voting method, for the purposes of this talk, is just a function which you give it a preference profile, and it hands you back a non-empty subset of the candidates in that profile. Okay? Also called a social choice correspondence, but voting method is shorter. And I want to tell you about this voting method called split cycle. So what split cycle does, we have this problem of cycles that prevents us from having a very clear winner. But what we're going to do is we're going to look at all of the candidates in the election such that they may lose to someone. So if I'm this X, I may lose to a Y. There may be some Y that has a positive margin over me, meaning Y beats me head-to-head. That doesn't necessarily exclude me as the winner, though. In the case where that YX edge in the graph, so Y does beat me, but it's the weakest edge in some cycle. So the idea is there's a kind of incoherence at the collective level. How should we resolve that incoherence? We should snip the weakest link in that cycle.
What is a weak link?
It's by the margin, by the weight of the edge. I'm going to show you examples. Okay? But you look at the graph, and even though I might lose to you, it may be that that victory of you over me is the weakest by margin victory in a majority cycle. And therefore, to kind of resolve the group incoherence, we're going to snip that weakest edge, and I'm still in the running to win. And I'm going to show examples of computing this in just a second. Yeah.
Do we know? Do we know that it can't be that in one of them the edge from me to you is weakest and the other the edge from you to me is the weakest?
Oh, we can't have edges. It's an asymmetric graph because if you beat me, I can't beat you.
I see.
By the way, I define the margin function. Yeah. Okay, so this particular, let's talk about some easy algorithms for computing this. One is if I'm X and I am losing, doesn't mean I can't actually be selected. If I'm losing head-to-head to Y, what we can do is we can use, for instance, depth-first search to try to find a path in the graph back from me, X, back to you, Y, each of whose edges has weight at least the margin by which you beat me. That would show that the margin by which you beat me is the weakest in a majority cycle. So it would get cut. Okay, that's one thing. We can do something else. We can use the Floyd-Warshall algorithm to compute for each pair AB the strength of the strongest path. By strength of a path here, I just mean the minimal edge weight along that path. And we get this matrix then, and then we can just check if the strongest path from me, X, to you, Y, has strength at least the margin by which you beat me. Okay. I'm actually going to illustrate the split cycle method using an inefficient kind of way of computing, not either of those methods, but I think for pedagogical purposes, this is helpful. So I'm just going to start with this graph, and the first thing we need to do with split cycle, for pedagogical purposes, is we'll identify the cycles. I'm not saying that this is how you should actually compute on a huge graph, finding all the cycles. Don't do that. But let's just do it in this example. So we see that there's the red cycle, the blue cycle, and the orange cycle. And then we just want to identify the weakest link in each cycle. So it's hard to see, but I've bolded the number on the weakest edge. So the weakest edge is 1 there, is 5 there, and is 3 there. Those things get cut. And then those edges do not count as genuine defeats because they're part of this cyclic incoherence. So we just snip those links, and we're left with this acyclic graph. And D is the only person who had no head-to-head losses. So that's just an example of what I mean by a voting method that uses voters' ordinal preferences to pick one or more winners, because there can be ties. I'm going to come back to that. Okay, now this turns out to have lots of great properties. So I'm not going to try to explain all these axioms. I'm going to explain some of these axioms, like I'm going to say what positive involvement and the Condorcet properties are. But when we started studying this, we started noticing that the split cycle method had a kind of unique, relative to the known literature, profile in terms of the axioms that it satisfied. So various other voting methods, they got blocked at various stages because they didn't satisfy certain good properties. And sort of only split cycle made it up there to the sort of holy grail, roughly speaking. But you can do much better than this. So again, with Eric Packett and one of my former students, Yifeng Ding, from the logic group here. So these are logicians. Eric is also a logician. We gave a complete axiomatic characterization that said that split cycle is the only voting method satisfying some list of nice axioms. Okay, so logicians love that kind of thing. So I think that this is a good voting rule, or some refinement of it. By refinement, I mean another voting rule that always picks a subset of the split cycle winners. Because sometimes there's a tie among the split cycle winners, and you might want to then have a principled reason for selecting a proper subset. Something like this is a good choice for voting in committees, like faculty committees or like student clubs or something like that, where people don't mind a somewhat sophisticated explanation of the voting rule. Now, I often get an objection that, oh, this is way too complicated to be used in politics. Yes, I concede, that's completely true. And so for political elections, I think we should use a simplified version, which not necessarily split cycle, but that still is based on these head-to-head comparisons. I think there are good reasons for thinking that this head-to-head comparison perspective is a good perspective on voting. We actually have an axiomatic characterization of the class of voting rules that only depend on the head-to-head margins. And I propose something very simple, which is we do look at the head-to-head performance of each two candidates. And we just, first of all, pick the candidate who has the most wins, the most head-to-head wins. In 99% or more of political elections, there's just going to be one candidate who beats every other candidate, and you're done. In the very rare case when there's not one candidate who beats every other, then you pick the candidate who has the most head-to-head wins. And if there's a tie for most head-to-head wins, then among those candidates, you pick the one who has the smallest margin of loss to another candidate. And I think this is fairly easy to understand. I mean, I went by very quickly, but you can make a one-page flyer that really explains this clearly to voters, and you don't need to talk about cycles and graphs and so on. Okay. Question? Yes.
It seems sort of the opposite of ranked choice, where sort of you can actually...
Yes.
So why would you argue that this is better than ranked choice?
Oh yeah, that's a long story. I kind of don't want to get diverted onto that during this talk, but let's talk about it afterward. I'd be happy to talk about it. So ranked choice, or what we prefer to call instant runoff voting, is where you iteratively eliminate the candidate who receives the fewest first place votes, and then you transfer votes accordingly. And that is not a method that's just based on these head-to-head comparisons. And we could do a detailed axiomatic comparison, and we could compare in terms of manipulability, we could compare in terms of social utility efficiency. It's like you could have a whole course on this comparison, but I don't want to get too far down that. So yeah, this is just to say that there are efforts. I'm on the board of this nonprofit that's trying to implement one of these kind of simple methods based on head-to-head comparisons of candidates in US political elections. So
Wes, when you spoke last time, you'd said some of these methods were being used in Virginia. There was an election in Virginia yesterday.
I didn't say it would be used in Virginia. I hope not.
I remember that as some talk you gave.
Yes, I think maybe what I had said is that certain forms of voting with ranked ballots, not yet the ones that I have proposed, but certain forms of voting with ranked ballots are definitely being used throughout the country, including in Oakland, San Francisco, Alaska, and so on. I don't remember about Virginia. I'd have to look it up. Yeah. Okay, so now I want to talk about just ways I've found computing very helpful for this subject. So this is mostly just a thank you. Like, thank you for providing the tools that has helped us study voting rules. So first is an obvious thing. It's like everything should be implemented, not only all the voting methods. So Eric Packett and I have this Python package called pref voting that we've been developing for a number of years now. And not only should all the algorithms be implemented for computing winners, but there's a lot of probability models for generating profiles, for generating those preference profiles. There are various algorithms for enumerating these objects up to isomorphism in some sense, or up to some equivalence relation. There are axioms. I keep referring to this idea of axioms, but I need to actually give you an example of an axiom. But an axiom is some property that a voting method could satisfy or violate in a given preference profile. Okay, so then all the axioms themselves should be implemented, and you should be able to check, here's a preference profile, here's a voting method. Does the voting method satisfy or violate the axiom in this preference profile? And so we have a big catalog of axioms, and we can auto-generate these big tables that show you whether the voting rule satisfies or violates the axiom, at least up to a certain number of voters and candidates that we've exhaustively checked, and so on. Okay, so that's the first thing, is just, and if there's students who are taking algorithms classes and want to figure out clever ways to optimize any of this, that would be very welcome. Here's a little QR code in case you want to get started. You can have a little tutorial on pref voting. The other thing that we did, since we're logicians, we immediately thought of formally verifying our proof. So we took that split cycle paper and working with an excellent undergraduate, EECS undergraduate, some of you may know Chase, formalized almost all the proofs in that split cycle paper in Lean. Okay, and of course Lean is a very hot topic nowadays. People are very interested in formalizing mathematics and also doing auto formalization. So I hope to continue this project of formalizing voting theory in Lean. Another thing that I found very helpful from the formal methods side of things is SAT solving. So I come from logic, so I teach basic idea of SAT solving in my intro logic course this semester. What we do is we come up with a formula of propositional logic that's satisfiable if and only if a certain voting method that satisfies certain axioms exists. Okay. So that's the basic idea. This is something that people had done in the computational social choice community before we did. We have a kind of interesting spin on how to use this, but so that can be used to prove an impossibility theorem, because you do the encoding, and by the way, like in this paper, we formally verify in Lean that encoding is correct, which is to say that we prove in Lean that that formula is satisfiable if and only if the voting method satisfying the desired axioms exist. That's a provable statement in Lean. And then we run the SAT solver, and it tells us, no, it's unsatisfiable. So boom, we have an impossibility theorem. We know that there is no such voting method. Okay. And then the little twist on this was that we developed some mathematical theory to say that if there were to exist a voting method satisfying certain axioms, then we can give a mathematical argument that there would have to be a voting method satisfying even stronger axioms that then make it really amenable to SAT solving. So like if you had just tried to use SAT solving on your original problem, it wouldn't have been that feasible. But once you do a little bit of math, you kind of reduce it to this much more feasible problem for the SAT solver. Okay, so I hope to continue using SAT, or fancier things. I mean, SAT maybe is not the fanciest thing that could be applied in this area, but it did work for us.
Is it for fixed numbers of voters?
Yes, it is for a fixed number. Yeah, the question was, is it for a fixed number of voters and candidates? Indeed it is. So when we prove these impossibility theorems, we can scale up to enough voters and candidates when we find the impossibility. Thanks. Now, yeah, I'm going to come back to that. So another thing we started doing recently was applying a little machine learning on the question of manipulation. So I think I already basically explained the idea of manipulation. There's this famous theorem called the Gilbert-Satterthwaite theorem that concerns voting methods that always pick a single winner. And basically any reasonable method it's not a dictatorship, and also it can have at least 3 possible outcomes, is manipulable. There does always exist a preference profile where some voter has an incentive to manipulate. In other words, the sincere preference profile where everyone casts their sincere ranking is not always a Nash equilibrium of this voting game. Okay. But the question that we asked, and other people have addressed this too, that in real life, you don't have full information about the preferences of all the other voters that would then allow you to make this smart unilateral manipulation. Unless we have a faculty meeting and I sit in the last position and I just wait for all my colleagues to give their opinions, and then I make the last move. But outside of that sort of setting, I have partial information, often in the form of polling that's published in the newspapers, about what the preference profile looks like. So, and I'm trying to strategize. Well, I always vote sincerely, but somebody could be trying to strategize on the basis of that partial information. So we were interested in whether neural networks, just MLPs, could learn to profitably manipulate. So we have a measure of how profitable your manipulation is in terms of how much it increases your utility. Could they learn how to profitably manipulate against various voting rules, given a probability model for generating the utility profiles, on the basis of partial information? So you only give the MLP that restricted amount of information about the preference profile, and you see whether it can learn to get really good, learn whatever the heuristics are for manipulating against the voting method. That was, to us, that was kind of illuminating, even though who knows what this shows about the capacity of humans, unaided by the neural networks, to manipulate, and that's a whole nother topic. Okay, and then the final thing that I want to talk about from tools that we've been using, well, it's just like high-performance computing, so Monte Carlo simulation. So I mentioned that there are these probability models for generating those preference profiles. And here's a very popular approach from political science. You place the voters and the candidates in some multi-dimensional space. So here's just two-dimensional space, using some multivariate normal distributions. This is a kind of polarized election. So we want to consider like sort of politically realistic kinds of probability models. And the voters are in blue and the candidates are in orange. And then the utility that a voter would get from the election of a candidate, this is the way political scientists have been thinking for a long time in spatial theory of voting, is some function of their respective positions. So it could just be the negative of the Euclidean distance, but the political scientists have considered much fancier things. So all of that is implemented in pref voting. And then a voter's ordinal ranking, this is assuming sincere voting. You could get fancier in adding manipulation on this, but we can ask, how good is sincere democratic voting at picking candidates according to a given voting method in terms of the social utility of the winners? So this is that sort of close to distortion in computer science, but we're looking at this average case analysis, and we're really just interested in the probability models and utility functions that the political scientists thought were plausible. Okay, now something about from social choice to computing. So we had a workshop, Vince Conitzer, Jobst Heitzig, and I organized a workshop at Berkeley in December of 23 that was called Social Choice for AI Ethics and Safety. And what came out of that was this ICML position paper. Social choice should guide AI alignment in dealing with diverse human feedback. So this was largely about post-training language models and about RLHF. And there's already an implicit kind of aggregation of human preferences going on there. But could you use tools from social choice to do some kind of more explicit aggregation, either for post-training or do something at inference time that used social choice? There's all kinds of like ideas that are thrown out. And now there's a literature on this where people, and there were independent groups that were also thinking about social choice for AI alignment or alignment of language models. So we have a conference series. In fact, if you have any work that's sort of relevant to this area of like many agents, alignment of AI systems, you should submit to our upcoming workshop, SC4 AI 26, which will be in Paris. I can give you the link afterward if you're interested. And then the final thing I want to mention is less about engineering AI systems, but more about finding out from the citizens what kind of safety specifications they would like an AI system to satisfy. How much risk are they willing to take? So this is a big project funded by ARIA in their Safeguarded AI program. And what's distinctive relative to everything I've talked about so far is here we're interested in people's attitudes toward risk, so attitudes toward risky probabilistic actions. So we want to somehow elicit their attitudes toward lotteries over social outcomes. Whereas so far I've just been talking about just selecting candidates or ranking candidates. Okay, I wanted to go fast for that because I want to get to my open problems here. I don't mean to be too grand by calling these open problems. They're just things that I haven't solved, or people that I know who've thought about and worked on also haven't been able to solve. But I think maybe one of them is explicitly computational, and the other, I hope, computational tools might help. Okay, so one important idea in voting theory has to do with the invariance properties of voting methods, like the amount of information that they need about a preference profile in order to compute the winner. Okay, so we'll say that a voting rule F satisfies majority invariance if whenever you have two preference profiles, if those two preference profiles have the same, what I'll call majority graph, which was like the margin graph that I had up before, but you just forget about the edge weights. All you care about is this person beat that person head-to-head, that person beat that person head-to-head. So you have an unweighted graph. if these two preference profiles have associated with them the same majority graph, then the voting rule must give the same answer for those two preference profiles. So the only information it cares about is the head-to-head win-loss kind of record. And there are various voting methods that have this invariance property. Okay. Something that uses more information, I'll call ordinal margin invariance, that says whenever you have two preference profiles that have the same ordinal margin graph. What is an ordinal margin graph? It's just like that margin graph I showed you, but you replace the edge weights with just the induced ordering on the edges. You say, this is the strongest victory in the election. This is the second strongest head-to-head victory. This is the third strongest head-to-head victory. So you don't care about the actual margins besides how they order the victories. That's what I'll call an ordinal margin graph. And there are some voting methods that are invariant with respect to that notion of invariance, including split cycle, right? If you think about it, split cycle was looking at the weakest link in the cycles. All that matters is the ordering of the edges. And I will talk about something called stable voting that has that property as well. And then there's full margin invariance where you're invariant toward the margin graph. So you have two profiles that have the same margin graph. You have to give the same answer, okay? And there's famous examples of these. So there's all these invariance notions. There are voting methods that satisfy that invariance property. I want to zoom in for my open problem here on the ordinal margin invariance. You might say, well, why are you zooming in on that? Well, one reason is just there's lots of popular voting methods that satisfy this ordinal margin invariance. That's one reason to zoom in on that. The other reason, I don't know how convincing this is, but I was trying to think of like normative arguments for ordinal margin invariance. And one is that if you have an election with many voters, then a small amount of noise in the collection of voter preferences, it's unlikely to change the whole ordinal margin graph. You know, if you drop a few ballots accidentally in on the way to taking them in or something, small changes, they may change the margins. Of course, they will change the margins. If you drop a ballot on the way to the administrative office, that will change the margins, but it won't necessarily change the ordinal margin graph. So there's a kind of robustness to noise. I don't know how convincing that argument is, but I thought I'd mention it. But now I want to see what happens when you take this ordinal margin invariance and you combine it with other influential axioms from voting theory. And now finally I can tell you about axioms. So first the definition. We're going to say that a candidate is a Condorcet winner if they beat every other candidate head-to-head, if they have a positive margin. So I'm the Condorcet winner if for any other candidate, more voters preferred me over them than vice versa. Okay, so it just means that in the graph, I have outgoing edges to all other candidates. That means I'm the Condorcet winner. And Condorcet, the philosopher mathematician, thought, yeah, you should pick the Condorcet winner if it exists. If it exists, the Condorcet winner should be the unique winner according to your voting method. So that's called the Condorcet winner criterion or axiom. There's also a kind of dual notion, which is the Condorcet loser. That's the person who has incoming edges from everyone else, loses head-to-head to everyone else. And one thought is, you don't want to pick the Condorcet loser. So it shouldn't be among the winners. Okay? So that's the Condorcet loser axiom. So I'm now giving you examples of axioms. Okay. Good. Condorcet loser says, do not pick a Condorcet loser. That's what the axiom says. Now I'm going to introduce some axioms a little more involved, but the basic idea is you want ties to be easily broken or rare. What could it mean for ties to be easily broken? It could mean that if you have a preference profile and your voting method picked more than one candidate as a winner, then you should be able to add a single voter that gets you down to just a unique candidate. Okay? Does that make sense? So ties are always like one vote away from being broken. That's what this says. You could strengthen this so to say that like every candidate who's tied could be made a winner by the addition of some ballot. But for my impossibility result, I actually want a weaker axiom because that's a stronger impossibility result. So this just says every tie can be broken by adding one voter. In terms of ties being rare, so let's consider this axiom, asymptotic resolvability. It says that for any number of candidates m, in the limit as the number of voters goes to infinity, the proportion of profiles, p, so it's just uniform distribution, the proportion of profiles p for that number of candidates for which your voting rule selects multiple winners, that goes to 0. So as you make the electorate very large, the probability that your voting rule will have a tie goes to 0. Does that make sense? So this is what I mean by ties are easily broken or they're rare, roughly speaking. And for practical purposes, you can see the appeal of these properties. Okay, so here's just a little lemma. It turns out that if you have an ordinal margin invariant method, and it satisfies either of these versions of resolvability, then what that implies is that if you have any margin graph, which is a tournament, which means between any two candidates, you do have an arrow, so you don't have any cases where there's no edge, and it's linearly edge ordered, so none of the margins are of the same size. You see how this has this nice property? So whenever you're in a linearly edge-ordered tournament, then you must select a unique winner. Okay, so that's what these resolvability properties imply. And so for this reason, let me just use the word resolvability in what follows rather than distinguishing between these two versions. Okay, so ties are rare. That's the idea that I want you to have. Okay, final axiom, not to bombard you with axioms, but the final axiom says, if some candidate X is the initial winner, and now you add to the election a new voter who ranks X uniquely first, then X should still win. So it says you shouldn't be able to cause a would-be winner to lose by showing up to the polls and ranking them first. And you may say, well, of course. Like, how could you ever violate that? No, but actually there's a lot of voting rules that violate that. Okay. So I'll just give you a simple example. So there's this Copeland voting method where you just give a candidate 1 point for every person that they beat, and -1 for every time they lose. And then if you just calculate the Copeland score in this election, C will be the Copeland winner. But if you add a new voter who ranks C in first place, but E in second place, that's actually going to help E more than it helps C, because Copeland doesn't care about the edge weights, it just cares about the win-loss performance. It actually doesn't change C's win-loss performance at all, but it does help E's win-loss performance a lot, and now E leapfrogs C and becomes the unique winner. That's a violation of positive involvement. Okay? So it sounds like an obvious axiom, but a lot of voting methods violate it. So you can make a table. I haven't told you about all these voting methods, but that's okay. I'm just saying you can take some common voting methods, and you can list which of these methods it satisfies or violates. Split cycle, by the way, violates resolvability. So you can have linearly edge-ordered margin graphs where a split cycle will pick multiple winners. And it's not guaranteed in the limit as the number of voters goes to infinity, unfortunately, that you'll get a unique split cycle winner. Okay. So when you see this kind of thing, the obvious question you ask yourself is, maybe it's impossible to satisfy all these properties. And indeed, that is the theorem of this paper that says there simply is no voting method, even already for 4 candidates. Already for 4 candidates, you run into this impossibility that you can't satisfy all these properties. Okay, let me skip saying something about the proof, although there's a little appearance of something from CS, is integer linear programming. And let me just ask, this is the open problem, which I don't know, is can you drop this ordinal margin invariance, which arguably was the normatively weakest axiom in this set? Can you drop that? What happens to the impossibility theorem? All of a sudden, is there now a voting method that will satisfy the remaining axioms? That would be nice. Or maybe it's still impossible, in which case we're sad. And then you could also think about adding margin invariance, which is weaker than ordinal margin invariance. Okay, you can try to use SAT for this, but it's actually not super effective because even if you find for a finite domain of profiles that it is possible to have a voting rule in the form of just a lookup table that satisfies these axioms, that doesn't show that you can have a voting rule for the full domain of all profiles of any number of voters and candidates. And also, what I want is a concise program, like a nice definition, like I had of split cycle, not a giant lookup table that says, in this election, pick that person, in this election, pick that person, in this election, pick that person. So one thing that I've been talking about with Emma from math, who's here, and with Sanjit, is maybe you can use some tools from formal methods, like maybe syntax-guided synthesis, some approach to program synthesis to make progress, maybe on this problem or on related problems. Okay, so that's a hopeful idea. And in the last 5 minutes, I want to explain the second open problem, which is about complexity. So this is about a voting method called stable voting. Stable voting is actually a refinement of split cycle, always picks among the split cycle winners, but it has that resolvability property. It's in daily use, so if you need to run a poll or something and you want a nice voting method for that, you can go to stablevoting.org. On a daily basis, there's plenty of polls that are being run. I'm going to, in this talk, define a simplified version of stable voting called simple stable voting. Okay. And the method is defined recursively in terms of the number of candidates. So it says if there's only one candidate in your election, then of course you just return the singleton set of that candidate and you're done. If there are many candidates, okay, then what do? You try to find the candidate X that has the biggest margin of victory over a candidate Y, such that if you remove Y from the election, so you go to the preference profile where you restrict everyone's rankings to the set without Y, then X would remain the winner after that removal. So you're looking for the candidate who has the best head-to-head performance against somebody such that if you were to throw them out, then in the smaller election, X would still win. So if you play the tape in reverse, you can see this voting method has this kind of stability property, which is if you win, and then you add another candidate to the election that you beat head-to-head by a lot, you're going to remain the winner, roughly speaking. That was sort of vague, but that's the basic idea of why we call it stable voting. Okay, and one naive algorithm is the following to compute this. If there's a Condorcet winner, somebody who beats everyone else head-to-head, it's easily provable that that person is the simple stable voting winner, so you just output that. If there's not a Condorcet winner, then you just enumerate the pairs of candidates, the distinct candidates, by descending margin. So you pick the biggest margin of victory first, and then the second biggest margin of victory. You just go down that list until you find some pair such that if we remove the second candidate, the Y, from the profile, we get down to a profile in which, when we do the recursive computation, X wins in the reduced profile. You find the first such margin M, and then you just output all the candidates X such that they beat some Y with margin M, and they still win in the subprofile after removing Y. Okay. And you do some memoization as you're going down the list so that you don't end up recomputing the answer for sub-elections that you've already computed. Okay, so let me give you an example of this. I'm just going to tell you, just trust me, that in this margin graph, A is the winner according to these various voting methods. We don't need to know what these are, but just think about stable voting. Okay, stable voting picks A. Now, suppose a new person decided to run in the election. And suppose that A crushes E head-to-head. Then you might have the intuition, well, then A should still win. This is a variable candidate axiom, or variable candidate idea, whereas positive involvement was a variable voter idea. So that's kind of intuitive, right? If A wins in the small election and you add this other person who A crushes head-to-head, shouldn't A still win? Some other voting methods actually change their answer and say, no, this would cause someone else to win. But here's what simple stable voting does. It says, let's consider the biggest head-to-head victory. Well, I made the example so that this is easy. The biggest head-to-head victory is A versus E, okay? And look, A wins after removing E from the election. Therefore, A is the simple stable voting winner. Let me make the computation just a little bit more interesting. I've just changed the edge weights so that the A versus E is no longer the biggest margin of victory, it's the second biggest. So then let's see what happens when we do this. So first, the biggest margin of victory is actually C versus E. So we consider removing E from the election, but when we remove E from the election, C does not win. Therefore, we go on to the next pair. And then now the next pair is the A versus E pair. We remove E from the graph, we're down to that graph, and then A is the winner in that graph. Therefore, by the recursive definition, A is the winner in the big graph. Does that make sense? Okay, that's simple stable voting. Now, this is computationally quite difficult. We can't scale this beyond maybe 25, 30 candidates in practice, so please, if your first visit to our website, don't try 30 candidates. So the question is, can you do better than this kind of naive recursive approach? So what's the complexity of this winner determination problem? I hand you a profile, I hand you a candidate. Is that candidate among the simple stable voting winners? I'm not a complexity theorist. You know, logicians like to prove decidable, undecidable, really undecidable, super undecidable. So please, complexity theorists, help with this. I mean, it's not even obvious that it's in NP because I can't give you a simple certificate proving that somebody's the winner that you can check in polynomial time. I know that's kind of a bad thing. But anyway, I think there's things to explore. And there's lots of other hardness results that people have proved for the winner determination problems for other voting methods. So there's a whole sub-literature of computational social choice that's all about proving hardness results for voting methods. Great, so I'm now at the end. I just want to conclude by saying, what have I argued, as we would say in philosophy in this talk? First, computational methods have been very useful for me. And if you look at that handbook of computational social choice that I put up at the beginning, that's a great book. So if you're interested in this, I would start there. I mentioned interactive theorem proving, SAT solving, machine learning, Monte Carlo simulations. I also very briefly claimed that social choice can be applied to AI alignment and AI safety, and of course, lots of other areas. So if you look in that COMSOC handbook, you'll see other applications. And then I just want to express my hope that new techniques from computer science, and especially work with computer scientists, which is why I'm so pleased to be invited here, can make progress on some of those open problems in social choice. So thank you so much for your attention.
Okay, we have time for questions. Any questions?
This is a question kind of outside of the computational topic here, but has Condorcet's tragic end reflected upon his legacy?
I don't know too much about the history, unfortunately. We were just chatting about this before the talk.
What version do you know
Yeah.
of his tragic end?
He didn't survive the terror.
Yeah, he was accused of being a Jacobin by the Girondins, and he was in prison, and his wife smuggled a poison pill. So that's the story. Is that what you...
I was going to say I'm going to start keeping one of these poison pills in my bag just in case I need it. Voting theorists getting persecuted here. Yeah.
Yeah, is there? So I presume there's a lot of discussion about the axioms. Like, for example, when you threw E in, it seems like, they were giving information about the other candidates, right? In some sense.
I missed the first part of the question. Can you repeat it?
There must be a lot of discussion about the axioms. Like
about the axioms?
Like when you got rid of that simple thing where this E liked the winner best.
Yes.
But kind of the fact that or E beat the winner, but he sort of, the information about E and the other candidates, it does provide you information.
Oh, yes, it does.
So it's not necessarily, these axioms are like...
The axioms are debatable.
Yeah.
Yes. So there are the mathematical facts.
Right.
And then there's the arguments, sort of philosophical arguments, about which axioms are normatively desirable.
Yeah, I was just talking culturally, I was just curious, what do you all spend your time doing?
Both. I mean, there's papers that are written that are purely mathematical, that just state the facts, or prove things. And then there's discussion also informally after talks about the normative status of the axioms. One thing I should say is that the modern perspective is, it doesn't just matter whether a voting method satisfies an axiom or not. If it violates the axiom, you really want to know, like, with what probability does it violate the axiom? And for that, you need some kind of probability model over preference profiles that hopefully is realistic to whatever your application area is. So it's not the end of the story if I say your favorite voting method violates this nice axiom, if it happens, extremely rarely in the domain that you want to use the rule. So that's another component of the normative discussion about the axioms.
Great. Okay,
Thanks.
one more question here.
First off, thank you for the presentation today. I learned a lot.
Thanks.
I had a question regarding, I know we glossed over this a bit, but could you give us a little bit more insight on how this theory could be used for AI alignment? Yeah, so the idea is, people don't all have the same preferences about how an AI system should behave. It's a very simple idea. People just have diverse, disagreeing preferences about how the AI system should behave. So there's got to be some aggregation. When you say that an AI system should act in a way that's beneficial to human beings, well, people have different views about what's good and what they prefer. So there's got to be some kind of aggregation. And you can either do it implicitly and not really analyze the kind of aggregation that's happening, or you can make explicit what kind of aggregation is happening and then ask questions about, is that a desirable form of aggregation? Could you do a better aggregation of human preferences? So that's the basic idea. Thanks.
Okay, one last question here.
Thanks, Wes, for the great talk. At the beginning of the talk, when you were setting up the space of problems here, you were talking about how there's a pretty rich set of ways that people might express their preferences.
Yes.
How ordered are they? Maybe they're weighted, and maybe you get the utility function or whatever it may be. But then it seems like in the back half of the talk we were sort of really focusing on this like weak strict order, and that's what the axioms and stuff framed are. So is that like the focus of this community, or like how little structure in these preferences do people care to study?
Great question. It's hard to say like sociologically what the main focus is. I mean, the reason so many people have looked at this case of ranked preferences is because that's actually being used right now in all kinds of places all over the world. People are going to elections and submitting rankings of the candidates. We do it in faculty meetings and so on. But people have also totally looked at this cardinal social choice, where you get some kind of cardinal information from the voters. So that's also a big thing. So I definitely don't want to diminish that. And in fact, in the AI safety project that we're working on, once you start asking people, like this is what happens in economics, once you elicit their preferences between more structured things like probability distributions, then you can infer, this is classical von Neumann-Morgenstern, expected utility or fancier things from behavioral economics. You can infer their underlying utility function or maybe some additional data that they use then, or you can represent them as using to make these pairwise choices and so on. So yeah, both are well represented in the social choice literature.
Cool, thanks.
Thanks.
Thank you, Wes.
Thank you.
Wes, can I have just I mean, this is a fantastic talk every time
Thank
you
you.
speak. But, here we are.
Yeah.
We still sort of live by this majority voting.
Uh-huh.
And by all the standards, this is like one of the worst things you can do. So, I mean, how do we reconcile our democracy based on majority voting when there is, everything you've said, majority voting is not?
Well, it depends what you mean by majority voting. So the one question is if you have just two candidates in the race, that's the really easy case for social choice theorists. There's May's theorem that characterizes majority voting. If all you can collect from the voters is their ordinal preference between two candidates, then there's May's theorem that says that majority voting is the unique voting method that satisfies some list of fairly plausible axioms. That's not about the electoral college. It's just about two candidates, and you have an electorate, and each of them expresses a preference between the two candidates. Then there's an axiomatic justification for majority voting in that context. That doesn't mean you shouldn't elicit additional information from your voters. And this is in the case of deterministic rules. You might start thinking about lotteries. I think there's plenty of room for innovation beyond majority voting if you expand the type of input that you're taking from the voters, or you expand the kind of output that you're willing to entertain. Yeah.
Fascinating.
Thank you very much.
Thank you again.
Thanks.
Keep